Hey, Honors Chemistry, Mr. Workman here. So it's looking like you maybe have another e-learning day for Tuesday, January 16th. In anticipation of that, I decided to come into school here on Monday, January 15th, and record a little video lesson here. Regardless, our plan for tomorrow would be for you all to start thinking about intermolecular forces of attraction in a little bit more detailed and deliberate way. And we would have you take care of this next practice quiz, AFL, Assessment for Learning, which covers Target 11. Pause the video lesson here now and take a look at Target 11 and make sure you understand what it is that it is intended for you to learn. Anyway, I'm here at DGS on a super cold day. It was super bright and sunny too, so I still have my sunglasses on. I got to be able to see what I'm doing. And I got my hat on. It's a little cold in the office even. So let me take you through how to approach this AFL. But before you watch the rest of the video, try it yourself first and then come back to this video if you're stumped or if you want to check your work. All right, here we go. So let me get my pen tool here and choose black. Methanol is the molecule in question here, CH3OH. That's the formula. I'm going to draw two of these molecules below, and I'm going to show you where the bonds are that have polarity. And then we're going to show intermolecular attraction with some dashed lines between these two molecules. And then, of course, we're going to name the type of intermolecular force and why it occurs. Let's get a little bit more space here. All right, so the way I draw these molecules, well, let's look back at the formula. If you recall, the way we draw structures, the first element is generally the central element, so carbon is the central element. And what's going to happen is three hydrogens are going to attach to that carbon, and then an oxygen and a hydrogen are going to also attach to that carbon. Now, this molecule is a little bit more complex because it has more than 5 atoms. So let me show you how this works. Let me get a little bit more space. Go back to the pen. All right. So I'm going to draw one molecule. I'm going to start with the central carbon, and then I'm going to draw connections with 3 hydrogens. So it's like I'm kind of starting out a tetrahedral shape here, and then I'm going to attach an oxygen to that carbon, and then this part of the molecule is going to have a bent shape. So it's kind of like a bent molecule mixed with the tetrahedral molecule. Now, if I'm going to go ahead and draw another methanol molecule, what I'm going to do is I'm going to show it in reverse orientation. So it's the same molecule, it's just that I'm reversing it, and that'll help me show you the intermolecular force of attraction in between the two molecules. Okay, let's identify the polar bonds. So I'm going to use red to indicate where there's polarity. The electronegativity value between carbon and oxygen is enough to create a little zone of polarity there. And the electronegativity value of oxygen and hydrogen is also certainly enough to create a polar bond there. So I'm going to go ahead and show that on both molecules. And the electrons are going to migrate or move toward the oxygen more than they would be around the hydrogen, and also more than they would be around the carbon. I had some students of mine in the last quiz incorrectly show that the carbon to hydrogen bonds would be polar. They're not polar. The electronegativity of carbon and the electronegativity value for hydrogen are not really that different. So when carbon and hydrogen bond, they share their electrons pretty fairly. I'm going to indicate a zone of partial charge here. So there's my little delta symbol with a minus sign, and I'm going to show a partial positive near that carbon, and I'm going to show a little delta with a positive near that hydrogen. And I'm going to do that over here on this molecule as well. So a partial positive area on that hydrogen, a partial negative on this oxygen, and then a little partial positive near that carbon. Now what I'm going to do is show with purple here, we'll go purple, is the force of attraction between the molecules. So this partial positive here on this molecule would likely have an attraction for the partial negative area on the oxygen atom of this second molecule. And then we'd have an interaction, an attractive interactive force on the partial negative area of this first molecule I drew, and the partial positive area on the second molecule I drew. And those intermolecular forces of attraction have a particular name. And the reason they have a particular name is that the bond between oxygen and hydrogen is very polar. Some bonds can be more polar than others. Oxygen and hydrogen, that's a pretty strong polar bond. And so what that sets up is a little bit stronger partial positive and a little bit stronger partial negative. And then therefore, the attraction between those little bit stronger partial positive and stronger partial negative areas can be a little bit stronger of a force. And so we have a special name for that. Let's indicate that, right? This is an intermolecular force of attraction. Let's call it what it is. Sometimes you'll see that abbreviated IMFA, okay, for intermolecular force of attraction. And this particular strong kind of intermolecular force of attraction, it's called a hydrogen bond. But what I like to do is put that word bond in quotation marks because it's not really a bond, right? It's called that, but it's not really a bond. Generally, we reserve the word bond for the intramolecular forces of attraction within inside a molecule, so in between the bonded atoms. This is a particularly strong kind of intermolecular force. It's a special kind of dipole-dipole intermolecular attraction. It is technically also a dipole-dipole intermolecular attractive force, but it's a special kind called this hydrogen bond. And generally we see that when we see hydrogen bonded to oxygen in molecules. And those molecules end up being pretty good at hanging on to themselves. That's also the same kind of intermolecular force of attraction that we see between water molecules. So methanol molecules hang on to each other pretty well, and as a result of that, tend to be liquid at the temperatures and pressures that we humans also exist at or can survive in. Despite it being a pretty small molecule, and despite it being very similar to methane, which is the name we give for natural gas, right? This oxygen here and the polar bonds inside those molecules and the asymmetrical nature of the molecule allows it to have these pretty strong intermolecular forces of attraction and remain as a liquid in the liquid phase, whereas a methane molecule would not be a liquid at the pressure and temperatures that we normally find ourselves in. Okay, so hopefully that makes a little bit of sense to you, and you're learning a little bit about hydrogen bonding and intermolecular forces of attraction and how to indicate that properly on molecular models that you draw. Okay, that's all for now.